Okay, this is the type of problem that's on the assessment, right? You got to have children on a merry-go-round doing dangerous things, right? So three regulation-sized children, 60 kilograms each, right, are initially at the edge, and the merry-go-round is initially moving at 23 RPMs. What is the resulting angular velocity? So half of this problem is just figuring out that darn moment of inertia. So let's do that. Okay, so before we've got the merry-go-round, and these kids are at the edge. They're right at the edge, right? So it's going to be 1/2 mr squared for the merry-go-round, right? Because it's a cylinder, and then the kids are going to be points, so it's going to be 3 mr squareds, right? So if they say there's something at a certain point, you just pretend it's just all of it is right there. Okay, so that's going to be 1/2. 210 is the merry-go-round. 2.56 squared, right? Plus 3 kids, 360 kilogram kids, each of them right at the edge. They're exactly on the edge. Come on, it's a physics problem. Okay, so what is that? So 0.5 times 210 times 2.56 squared plus 3 times 60 times 2.56 squared is 1867.776 approximately kilogram meters squared. So this is before, right? Okay, so let's draw a picture. We got to do after. Right after, they are 0.5 meters from the center, right? So afterwards, here's the center, and here they are. They're very close to the center. Okay, so it's going to be 1/2 mr squared. So the merry-go-round itself doesn't change. It's still a 210 kilogram, 2.56 meter radius uniform cylinder, evidently, right? Okay, but the kids are going to change, right? So there's 3 mr squareds, right? And that r is going to be 0.5. That's the only difference in this calculation. So 1/2, 210. Like, are we done with this problem yet? 2.56 squared plus 3 times. That's 2.56. I don't know what that is in there. Okay, 3 times 60 times 0.5 squared. Will that change it a lot? Let's find out. Am I just going to go up arrow and be so lazy as to change the 2.56 to 0.5? $733.128 kilogram meters squared. So this is our after moment of inertia. And now we're ready to do the problem, which is really a pretty simple problem. Okay, I1 omega 1 equals I2 omega 2. So let's see, I1 is this guy, right? Kilogram meters squared, right? And then omega 1. Notice that that we're just going to solve. I can, as long as these are the same units, I can use RPMs and RPMs, rotations per second, anything I want, radians per second. I'm just going to throw RPMs in there just for kicks. 23 RPMs is equal to our new moment of inertia, 733.128 kilogram meters squared. And then omega 2 is what we're solving for. Now notice, if I put RPM in here, this is going to come out as something RPM. Okay, so let's do this. We can do this. So 1867, that guy, times 23 divided by the 733.128. And I get 58.59. 596 RPMs. Ta-da. All right. Yeah. So basically, the only trick, I think people just mess up on the figuring out this new moment of inertia, right? Okay. And then, the teacher doesn't even write it correctly, right? That number there is a 2.56. All right.